Okay, everybody, this is going to be going over the Unit 1 practice test. Okay, so you have your Unit 1 test coming up and you need to review. So I posted a practice test and I posted the answer key, but what I'm going to do in this video is kind of go through it and maybe explain it a little bit more in detail to make sure you understand what's going on. But as you prepare, remember, don't sleep on the checklist. So make sure you go into the Unit 1 test review folder and look at the practice test, look at the key, maybe watch this video, but go over the checklist. Everything that's on the checklist will be on the Unit 1 test. So don't, act surprised when something shows up on the test and it was on the checklist. So we have a little bit of time here to make sure we review, but you got to take advantage of the time and review. All right, so let's look at the practice. Well, again, first, make sure you understand. Look at the checklist. All right, be able to do all of this stuff that's on the checklist. Okay, so let's go ahead and look at the practice test. This is pretty much how your Unit 1 test will look. All right, it's going to be all free response. There is no multiple choice. You get all your multiple choice practice with the concept checks. And as we get closer to the final exam and AP exam, you'll have practice exams that you'll be able to do and get more practice with the multiple choice. Okay, so all of our unit tests are going to be free response. And the way it's going to work is you're going to put all your answers on separate sheets of paper. So when you come in, there's 5 questions. I'm going to give you 3 pieces of paper to start with. Every time you finish a question, you can move to the back. You use a new sheet of paper, but you can go front and back. So like if I do question 1 on the front of a piece of paper, then I can start question 2 on the back of that piece of paper. And if I finish question 2 on the back there, then I'll move on to a new piece of paper to question 3 and so on. Okay. But also notice that in the instructions it says these actual questions here will be answered directly on the test. Okay, so you can write on this and all that stuff, but make sure you're putting your answers on the separate sheet of paper that you get, except for when prompted to actually write on the test itself. Okay, like so it says 2A right here, 2A, where you're drawing these dot structures, you're going to be putting them right here on the test, but answering the rest of these questions down here, you're going to be writing those on your separate sheet of paper. All right, so let's go through it. All right, so we have a list of substances and we need to rank them from highest melting point to lowest melting point. So it's going to be the highest on the top and the lowest on the bottom. So remember, we want to separate these in terms of do we have any network covalent things, then ionic, then metallic, then polar covalent, then non-polar covalent. So the first thing I would notice is I have a network covalent, so I know carbon, graphite, that's going to be number 1. And then we would highlight any of the ionic compounds. Then I would look at the ionic compounds, and I would rank those in terms of Coulomb's law. So between sodium chloride and sodium fluoride, I know that sodium fluoride would be stronger because fluoride is a smaller ion than chloride. But then if I'm comparing magnesium oxide to sodium fluoride, magnesium is a smaller ion than sodium, but fluoride is a smaller ion than oxide. So the distance between these 2 ions versus those 2 ions is probably going to be relatively the same. But the reason why this is going to be stronger is because magnesium's 2+ and oxide's 2-. So 2+ is going to be more attracted to a 2- charge versus a 1+ and a 1- charge. So again, number 1 would be the graphite. Number 2 would be magnesium oxide. Number 3 would be sodium fluoride. And then we would have sodium chloride. So let's look at the key and see if that's what we got. Yep, so we got graphite, magnesium oxide, sodium fluoride, sodium chloride. Okay. Then we would look for any metals. And I don't think there are any on this one. So yeah, no metals. So what's left? We got H2S, we got H2O, we got methane, and we got propane. Okay, so we should know that H2S and H2O are both polar because they would have the same exact shape. They're both bent. Sulfur and oxygen are in the same group, so they would look the same way. So this is bent, and this is bent. They both have polar bonds, HS is a polar bond and HO is a polar bond. But this is polar with Fon, so water has hydrogen bonding, and this is polar without a Fon bond, so this would just have dipole-dipole interactions. And so we would expect the water to be the next strongest, and then the H2S. And then we have the propane and the methane. They're both nonpolar because hydrocarbons are just going to be nonpolar all the time. And but this would have a bigger carbon chain and a bigger electron cloud, more electrons. So this would have stronger London dispersion than the methane. So methane would be at the bottom, and then propane would be number 7. So let's go ahead and look at the key. So we got the water because of the hydrogen bonding. We got the H2S, dipole-dipole interactions. Then we got the propane with the stronger London dispersion over the methane. Okay, so that's number 1. And the other thing to remember is when you're taking the test, you're going to have a formula sheet. And remember, for this unit, the basic formulas you're going to need are the light formulas. And you're also going to have to know what a mole is. So don't forget about Avogadro's number there. Okay, and you'll get to... you'll see an example with Avogadro's number here in a second. All right, so let's go to number 2. All right, so drawing the dot structures. So CF4, we know that's going to be just tetrahedral. So carbon, single bonds to the four fluorines, and each fluorine would have 3 lone pairs on them. The thing to quickly get is selenium has 2 more valence electrons than carbon, right? Selenium is in oxygen's group, not carbon's group. So if this was silicon, then this would be tetrahedral as well. It would be the same thing. But the selenium has 2 more dots. So this is going to have 4 bonds and also a lone pair on the central atom. So let's go ahead and look at the dot structures there. All right, so quickly we could draw the CF4, and then, quickly we could also draw the selenium tetrafluoride, a lone pair on the selenium with the 4 single bonds. And that's okay for selenium. Remember, selenium can have an expanded octet. Okay, the very next question they ask is identify the shape and the hybridization of each molecule. So tetrahedral, and this would be seesaw. And then remember the hybridization counts, we just count the domains around the central atom. So 1, 2, 3, 4, so that's sp3. And then here we got 1, 2, 3, 4, 5, so sp3d. All right, so we keep going. It says CF4 has 0 dipole moment, so they're telling you CF4 is nonpolar, whereas SEF4 has a permanent dipole moment. That's telling you that SEF4 is polar. Account for this observation. Well, remember, it's about symmetry, so CF4 tetrahedral is a symmetrical shape as long as all the ligands are the same. But selenium tetrafluoride has a lone pair on the central atom, and that's going to make it asymmetrical. So something along those lines. Let's see what we said in the key. CF4 is symmetrical, therefore it will not have opposite dipoles, or it won't, be polar. Selenium tetrafluoride is asymmetrical due to the lone pair on the Se on the selenium. Therefore, it will have opposite poles, a positive and a negative dipole. Okay, so something along those lines, explaining why this one is symmetrical, this one's asymmetrical, that kind of thing. They both have polar bonds. All right, so let's go to the next one. The CF bond has a bond energy of 435, where the SEF bond has a bond energy of 375. So why is the CF bond stronger than the SEF bond? Okay, so the first thing I would go to is, I would say the CF bond is more polar than the SEF bond, right? Maybe a bigger electronegativity difference. That's what I would be thinking. But you might remember from your concept check that selenium and carbon have basically the same electronegativity value. So actually these bonds are equally polar. So what would account for this bond being stronger than that bond? They're both single bonds, so it's not the difference between a single and a double bond. It would be, in fact, it would be that this bond is shorter than that bond. And you know that because carbon is a smaller atom than selenium. So this bond length would be shorter than that bond length. Okay, but because you weren't told the electronegativity values, if you said that there was a bigger electronegativity difference between carbon and fluorine versus selenium and fluorine, you would still get credit for that in saying the one is more polar than the other. You don't have to know that carbon and selenium have the same electronegativity value. So it would be the better answer is because selenium does and carbon do have the same electronegativity value. So the bond length between carbon and fluorine is shorter than the bond length between selenium and fluorine, which makes sense because carbon is smaller than selenium. But this would count because they didn't give us the actual values of electronegativity of carbon and selenium. So if you had said the CF bond is more polar, then that would be an acceptable answer as well. Okay, but this one is the better one due to the fact that the bonds are equally polar, same electronegativity difference. So what would make this bond stronger? Bond length in this case. Okay, shorter the bond, the stronger the bond. All right, so now they tell us the bond energy again. Now understand what this says. This is 435 kilojoules per mole. So it's energy per mole of bonds. Okay, we want to calculate the energy of just one bond. So this is the energy for a mole of bonds. This is asking just to break one bond, what would be the energy? So, and notice that it asked for in joules and we were given kilojoules. So this is just dimensional analysis. So this is when Avogadro's number is going to come into play. So first thing I would do is convert my kilojoules to joules. All right, so multiply by 1,000. And then to get rid of per mole and get per bond, it's 1 mole of bonds for every Avogadro's number of bonds. So if we divide that number by Avogadro's number, this would be the energy for just one bond, one individual carbon to fluorine bond. So it should be a small number because we're talking about one little covalent bond. This bond energy, the 435 kilojoules, is for a mole of those bonds. All right. So this would be the energy in joules for one bond. Okay. So we'll keep going. Then it says, what is the wavelength of light? That would be, it would have the minimum amount of energy required to break one of these bonds. Okay, so, well, we just calculated the energy required to break it. Now we're going to use these equations and solve for wavelength, right? So we can plug in our energy and solve for the frequency. And then once we have the frequency, we can solve for the wavelength because the speed of light, c, is given to us over here. Planck's constant is given to us over here, so we can just use those. Or we could remember our shortcut equation, which is E equals hc over lambda. So if we solve for lambda, which is wavelength, it would be lambda equals hc over E. So plug in Planck's constant, plug in the speed of light, plug in the energy value that we just calculated, and that's going to give us meters. If you use times 10 to the 17 here for the speed of light instead, that would be nanometers. And then the very next question on the test asks, would we be able to see it? And remember, our visible range is between around 400 nanometers and 700 nanometers, and this falls out of that range, so no, we would not be able to see it. It's too short. We can see 400 nanometers, but we can't see 275 nanometers. All right? Okay, let's move on to number 3. All right, so PES, so before I even read the question, let's just mark it. Like first, look, we got 647 times 10 to the negative 18 to 0.98. So this is the larger binding energy to weakest binding energy. So we would read left to right, 1s2, 2s2, 2p6, 3s2, 3p6, and then this would be 4s2. Okay, so we recognize this as calcium, and it says to write the electron configuration for calcium. So I just kind of said it and identify the element. So let's go to the key. Now notice it didn't say write the full electron configuration. So you would be okay to write the shorthand over here, but that would be the electron configuration. And you could, it says identify the element. So it didn't say name the element. So you could name it and say calcium, or you could just write the chemical symbol. Okay. Next question. Calculate the wavelength in meters of light, electromagnetic radiation, so light, needed to remove an electron. So from the valence shell. So here is the valence shell, and this is the ionization energy for one electron. Notice the x-axis is binding energy per electron. So that's why this is such a small number, because it's talking about an individual electron being removed from the atom. And it's not proper scientific notation, but that's okay. 0.98 times 10 to the negative 18. So again, we're going back to our speed of light equation and our energy equation. And we're just plugging in the energy value. And the energy value we're plugging in is that 0.98 times 10 to the negative 18, which is on the PES spectrum. And we get our wavelength in meters. Okay. So let's keep on rolling. Here we're given another PES. So this would be 1s2, 2s2, 2p3. Notice each line on this axis would represent an electron. 1s2, 2s2, so 2p3. So the element is nitrogen. Remember, nitrogen has 5 valence electrons. Be careful. A lot of students will say 3 because of this peak, but remember, the valence electrons are the s and the p electrons. So 2s2, 2p3, so 2 plus 3, 5 valence electrons. Is it paramagnetic or diamagnetic? It's paramagnetic because it has unpaired electrons, right? In that 2p sublevel, it's going to be up, up, up. So it's going to have 3 unpaired electrons. And anytime you have 1 or more unpaired electrons, you're paramagnetic. Diamagnetic, all your electrons are paired. So let's go to the key and just make sure. So nitrogen, 5 valence electrons, it's paramagnetic because it has 3 unpaired electrons. All right, and then the next question is identify 2 ways that the PES for carbon would be different. So remember, carbon is just, one space to the left on the periodic table. It has 1 less proton. So first of all carbon's peaks would be the same height. So carbon's third peak would be the same height as these two. So it would have 3 peaks just like nitrogen, but its third peak would be shorter, okay? It would be the same height as this peak and this peak. It would be identical, but all of its peaks would be shifted to the right. All the peaks would suggest lower binding energy because carbon has 1 less proton in the nucleus. All right, so let's see. Its rightmost peak would be the same height of the first 2 peaks. The peaks would all be shifted to the right. There you go. And if you had to explain why, you would say because it has a smaller nuclear charge, and so all of the electrons would not be as tightly bound to the nucleus as the nitrogen atom. Okay. All right, number 4. So they give us this compound urea. They give us the dot structure for it. Identify the hybridization of the valence orbitals of the carbon atom. So you go to the carbon atom, it has 3 domains around it, so sp2. All right, then part B, what is the shape of each nitrogen? If you look at each nitrogen, they're kind of identical here. 3 bonding pairs, 1 domain, 1 lone pair. So each nitrogen would be trigonal pyramidal geometry. So, okay, and so let's go to the key and make sure we got that. Whoops, here. All right, so the carbon was sp2 because it had 3 domains. Each nitrogen's trigonal pyramidal. And then if we go to the next question, it's saying draw 1 dashed line to indicate a possible location of a hydrogen bond. So here's a nitrogen and nitrogen bonded to hydrogen. So that would be a positive dipole there with a Fon bond, right? And so I could draw a dashed line from the oxygen of the water to that hydrogen. That would be a hydrogen bond. If you wanted to, you could have like maybe this hydrogen here connected to that nitrogen, because that would be a Fon bond dipole attracted to a negative dipole, so maybe a dashed line there. You could also have like maybe this hydrogen dashed line interacting with that oxygen. Now I know that oxygen is not a part of a Fon bond, but this hydrogen is part of a Fon bond. So that negative dipole interacting with that positive dipole, that would also be classified as a hydrogen bond. So there's a lot of different places you could put it, but remember it just says draw 1, and that's all you need to do. So again, I have my oxygen from my water interacting with the hydrogen that's attached to the nitrogen on the urea molecule, and there you go. All right. So we'll keep going. So here is kind of a representation of lithium chloride. It's just saying identify the big sphere, identify the small sphere. So the small sphere, the black one, would be lithium plus, because lithium plus is smaller than chloride 1 minus. And the way you should think about this is you should know that lithium 1 plus is smaller than helium, and chloride 1 minus is actually larger than argon. So you should know that lithium is the smaller ion. So you would write Li plus here, and you would write chloride 1 minus there. So let's go to the key and see if that's what we said. Yeah, okay, basically. All right. But if you were writing this on your test, right, you would have Cl minus, or sorry, lithium 1 plus here and Cl minus here. All right, so this question's basically just asking why is magnesium hydroxide's melting point or lattice energy stronger than strontium hydroxide? So they're both ionic compounds. So it's why is this ion to ion interaction stronger than that ion to ion interaction? And it's just because magnesium's smaller than strontium, basically. So Coulombic attraction, the magnesium ions can get closer to the hydroxide ions. So ionic radius increases as you go down a group on the periodic table. Magnesium 2 plus is smaller than strontium 2 plus. This means magnesium 2 plus ions can get closer to the hydroxide ions, and the shorter the distance between the opposite charges, the stronger the attraction. So that just increases the Coulombic attraction. I threw in the word Coulombic there because it said mention Coulomb's law, so there you go. So that works. All right, so number 5, we did this example in class, but it's just why is this the better structure than that? So make sure you review how to calculate a formal charge, but essentially this has a formal charge of 0, 0, positive 1, negative 1. So in this structure, the positive formal charge, positive 1, is on the nitrogen, and the negative formal charge is on the oxygen. But if we go here, we got 0, we got negative 1 for the carbon, positive 1 for the nitrogen, and 0 on the oxygen. So the reason why this is better is because the negative formal charge is on the more electronegative element. So it has the same amount, right? We don't have a formal charge where they're all zeros, but remember, if you're ever going to have any negative formal charge, it's got to be on the more electronegative element, and that's why this one's better. So let's see the key. So here in the key, I've identified the formal charge on each element in this one and each one in this one. And so remember, this one puts the negative formal charge on the more electronegative element, and that's what's kind of explained in the key there. Okay. So for the dots, dot structure here, remember, halogens are only going to have single bonds, so you'd have a single bond here, a single bond here. And let's start off with a single bond between the sulfur and the two sulfur atoms. So single bond, single bond, single bond, and then fill in the lone pairs. So 3 lone pairs on the chlorine, 3 lone pairs on the chlorine, 2 lone pairs on each of the sulfur to make sure they have at least 8, and see if that matches the number of total electrons. So sulfur is coming in with 6, so you got 6 times 2, that's 12, and then you have plus 14 for each of the chlorines. So 12 plus 14 is 26 dots. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. So that gives us our dot structure. So I've kind of explained it in words, but this would be the structure. That's all you would need. And then they ask for this bond angle here. And just remember, it is not 180, even though we drew it that way on the test. It's really 109. If you wanted to say 105, that would be better. But remember, whenever you have 4 domains around an atom, we're going to say the bond angle is 109. Okay? And I think I skipped one, so let me go back and see which one I skipped. Sorry. Here we go. Oh, it asks for the hybridization of the carbon in both structures are in the correct structure, so 2 domains, so just sp. In this structure, it would have been sp2 because it has 3 domains, but in the correct structure, it has 2 domains, so sp. All right. All right, so this one we have, it gives us this reaction, and then, you got all this stuff. Now, this is going to be an important thing here that we look at, but first it just says identify the intermolecular forces in HCl, identify the intermolecular forces in CCl4. Remember, everything has London dispersion, okay? So HCl is polar, but it doesn't have a bond bond, so you would say dipole-dipole interactions and London dispersion. CCl4 would be nonpolar because it's symmetrical, all the ligands are the same, no lone pair on the central atom. So all this has is London dispersion. So if we list them, right, dipole-dipole interactions and London dispersion forces for the HCl, only London dispersion for this CCl4, okay? Now, let's stress something here, okay? If this explanation wasn't given right here, and they just said, which one of these, HCl or CCl4, would have the higher boiling point or just stronger IMFs, then if you weren't given this information here, then yeah, you could say probably HCl because it has dipole-dipole interactions and London dispersion, whereas the CCl4 only has London dispersion forces. You could make that argument, but that's not the case. You are given this statement. It's telling you as you cool these two gases, this one condenses where this one remains a gas. So at the same temperature where this is a liquid, this ends up staying a gas. So that's telling you that this one has weaker IMFs, okay? And so all you have to do is say the HCl, based on this statement above here, HCl has weaker intermolecular forces, or you could just say, you know, the dipole-dipole interactions and the London dispersion in the HCl is weaker than the London dispersion forces alone in CCl4, okay? So let's look at the question. We know the London dispersion forces in CCl4 is stronger than the combined dipole-dipole interactions and London dispersion in HCl. There we go. All right. So I hope that helps you prepare for the test. The test will be very similar. So hopefully you feel good about it and come in ready to, you know, get an awesome grade. All right. So have a good one.